Welcome to Comparative Anatomy. Today, we are going to explore two of the most fascinating sensory organs in the mammalian body, the eye and the ear. We will uncover how biology and physics work together perfectly to allow mammals to see their environment in sharp detail and hear the faintest of sounds. Let us dive in. Let us begin by looking at the mammalian eye. Imagine you are holding a highly advanced digital camera that can automatically focus, adjust to different lighting conditions, and capture images in stunning three-dimensional detail. The mammalian eye is exactly like this camera, but far more sophisticated and built entirely from living tissues. When you look at a beautiful sunset or spot a fast-moving object, your eye is instantly gathering light rays and bending them to form a clear picture. Understanding this biological camera shows us how perfectly anatomy is designed for survival. To understand how this biological camera works, we must examine its parts. The mammalian eye is a complex, fluid-filled spherical organ consisting of three main layers. The tough outer layer is the sclera, which includes the clear cornea at the front. The middle layer is the vascular choroid, which provides essential nutrients to the eye. Finally, the inner layer is the retina. This is the light-sensitive screen containing specialized photoreceptor cells called rods and cones. These layers work in perfect harmony to ensure that light is captured and processed with incredible speed and accuracy. Now that we know the layers, how does light actually travel through them? Light enters through the clear cornea, passes through the pupil, and is focused by a flexible crystalline lens onto the retina. Vision is arguably the most critical sense for many mammals, playing a massive role in daily survival and navigation. The true magic lies in the ability of the lens to change its shape. This process, known as accommodation, allows mammals to focus seamlessly on both near and distant objects. If this system fails, it can lead to severe visual impairments. To truly appreciate how the lens accommodates, we must look at the physics of optics. The eye acts as a biological lens system that bends incoming light rays. We use the thin lens equation to relate three critical variables. The formula states that 1 over the focal length equals 1 over the object distance plus 1 over the image distance. The focal length represents the bending power of the lens. The object distance is how far the item is from your eye. The image distance is the fixed anatomical distance to the retina. If an object moves closer, the object distance decreases, meaning the lens must bulge to decrease its focal length and keep the image perfectly sharp. Let us see this formula in action with a real-world scenario. Imagine a student reading a textbook held 0.25 meters away. The internal distance to the retina is fixed at 0.02 meters. We need to find the required focal length. We substitute our known values into the thin lens equation. The incoming light requires a power of 4 diopters, and the internal eye distance requires 50 diopters. Adding these gives a total optical power of 54. Taking the inverse, we find the focal length is approximately 0.0185 meters, or 18.5 millimeters. This tells us exactly how much the ciliary muscles must contract. Having calculated how the lens focuses light, let us visualize this entire system. Here you see a cross-section of the mammalian eye. Notice how incoming light rays enter from the left, passing through the transparent cornea. They travel through the pupil, which is controlled by the iris, and hit the crystalline lens. The lens bends these rays, sending them through the vitreous body to converge perfectly on the retina at the back of the eyeball. From there, the optic nerve carries the electrical signals to the brain. This beautiful system proves that anatomy and physics are deeply intertwined. We have seen how mammals process light, but what about sound? Think of the mammalian ear as a highly sensitive biological microphone connected to a powerful mechanical amplifier. When a friend speaks to you, they are creating invisible ripples of pressure in the air. Your ear's job is to catch these tiny, invisible ripples, amplify them, and turn them into electrical signals that your brain can understand. It is an incredible journey from sound waves in the air to fluid waves inside your head. We will break down this journey step by step. Just like the eye, the ear is divided into specialized anatomical zones. It is divided into 3 distinct regions. The outer ear consists of the visible pinna and the ear canal, which funnel sound waves toward the eardrum. The middle ear is an air-filled cavity containing 3 tiny bones called ossicles, the malleus, incus, and stapes. Finally, the inner ear contains the fluid-filled cochlea for hearing and the semicircular canals for balance. Specialized hair cells inside the cochlea convert mechanical vibrations into nerve impulses, allowing mammals to communicate and detect danger from all directions. This intricate structure is necessary because the ear faces a major physical challenge. The middle ear must solve the problem of transferring sound energy from low-density air into the high-density fluid of the inner ear. Without a way to amplify the sound, most sound waves would simply bounce off the fluid of the inner ear, leaving the mammal practically deaf. The middle ear ossicles act as a mechanical bridge, ensuring that the delicate vibrations in the air are successfully transmitted into the heavy fluid. This amplification is absolutely crucial for a mammal's survival in the wild. To solve this physical challenge, the middle ear acts as an acoustic transformer. We use the fundamental pressure equation, where pressure equals force divided by area. Because the force remains roughly the same as it travels through the ossicles, the pressure is inversely proportional to the area. This leads us to the amplification ratio formula. The ratio R equals the area of the eardrum, A1, divided by the area of the oval window, A2. If the area decreases, the resulting pressure will increase dramatically. The mammalian ear uses this exact principle by taking the force collected over the large eardrum and concentrating it onto the tiny oval window. Let us put some real anatomical numbers into this ratio to see the mechanical power of the ear. Suppose a sound wave hits the eardrum, which has a surface area of 55 square millimeters. The force is transferred to the oval window, which has a much smaller area of only 3.2 square millimeters. We set up our ratio by dividing 55 by 3.2. The units of square millimeters completely cancel out, leaving us with a pure multiplier. The calculation gives us a final result of approximately 17.2. This massive amplification is exactly why mammals can hear faint rustling leaves. Now that we have used this amplification formula, let us understand exactly where it comes from. We start with the fundamental physics equation for pressure, which states that pressure, P, equals force, F, divided by area, A. We can write this equation for 2 different locations in the ear. First, the pressure at the eardrum is the force at the eardrum divided by its large area. Second, The pressure at the oval window is the force at the oval window divided by its much smaller area. This sets up the mathematical foundation to compare the two pressures. Continuing our derivation, we look at the role of the tiny middle ear bones. For simplicity, we assume the force transferred by the ossicles remains constant throughout the transfer. Therefore, the force at the eardrum equals the force at the oval window. When we divide the pressure at the oval window by the pressure at the eardrum, we create a ratio of 2 fractions. Because the force is the same in both the numerator and denominator, it completely cancels out. We are left with the inverse ratio of their areas. This proves mathematically how concentrating force into a smaller space increases the overall pressure. So, we have proven how the ear amplifies sound mathematically. Now, let us see the actual anatomy that makes this possible. In this diagram, you can trace the path of sound. Waves enter the outer ear and travel down the canal to strike the large tympanic membrane. Look at the middle ear, where the 3 tiny ossicles connect this large membrane to the much smaller oval window. This visual perfectly illustrates the area reduction we just calculated. Finally, the amplified waves enter the coiled cochlea in the inner ear. This masterpiece of biological engineering seamlessly blends acoustics and mechanics. We have covered a tremendous amount of ground today, so let us review the most important ideas. First, the mammalian eye acts as a biological camera, using a dynamic lens to focus light onto the retina. We saw how the thin lens equation dictates the exact focal length required for clear vision. Second, the ear is an acoustic transformer that converts air pressure waves into amplified fluid waves. By concentrating force from the large eardrum onto the tiny oval window, the middle ear massively increases sound pressure. You now understand the beautiful physics behind mammalian sight and hearing.